We now want to do the final part of the algorithm, the area minimization, where we get a planar orthogonal drawing from our orthogonal representation. So the problem we want to consider is the following, the compaction problem. We're given a plane graph with maximum degree 4 and an orthogonal representation of the graph, and we want to find a compact orthogonal layout, so a drawing, that realizes this representation. First, we want to look at a special case where all the faces are rectangles. For this case, there are some guarantees that are possible. Where we can guarantee a minimum total edge length and minimum area. And for that, we make use of some very specific properties. In particular, the bends that we have only lie on the outer face. Also, the opposite sides of a face always have exactly the same length. And we want to formulate this as an ST flow network for the horizontal and the vertical compaction. So let's have a look at one example here. All the faces are really rectangles, and the outer face looks like this. We want to define a horizontal flow network first that gives us the length of the horizontal segments. Our vertex set are all the faces of the graph without the outer face, but then we add a source and a sink on the outer face. So the outer face is basically here twice. And the edges correspond exactly to these horizontal segments. So we have an edge from one face to another one, if and only if there's a horizontal segment between them and this face lies below the other. So we get from S these three segments, so these edges, and these edges, and so on up to T. And then we also add an edge from T to S so that we can close the circulation. We now have to define these values. So what is the lower bound for all these edges? Well, every segment must have length at least 1, so the lower bound is a 1. What is the capacity of all these edges? They can be as long as we want, so the upper bound is infinity. What should be the cost? Well, the cost is exactly 1. So for every unit of length, we get 1 unit of cost. And finally, what is the production and demand of our vertices? Well, for all those interior vertices, it should be exactly 0, because the length at the bottom and at the top of the rectangle has to be exactly the same. And for S and T, we also set it to 0. So we have this extra edge TS here that will cancel out what the source gave out here and what the sink took in there. So this whole thing is a rectangle. That means if the sum of these segments here is a 10, then what comes out here is also a 10. And then this edge gives a 10 back to S, so that everybody has their production and consumption 0. And we do exactly the same for the vertical segments, and we get the vertical flow network, where we go from left to right through the vertical segments. And now the nice thing is that a valid min-cost flow for these two networks exists if and only if the corresponding edge lengths induce orthogonal drawings. So from these numbers, from these flows that we get, we can immediately read off the length of these segments. And if we put these together, then we just get the coordinates of the vertices and we immediately have a drawing. Now 2 more questions for you. What do these 2 numbers here represent? Now this is the total width and this is the total height of the drawing. This is the sum of the flows going out here or coming in here. This is exactly the width. And what do these numbers here represent? This is the total edge length. This is just summing up the flow of all the segments, and doing that you get the total edge length of the drawing. Now the thing is, in general this will not be the case. Now our faces will not always be rectangular. We still want to use this approach to solve it. So what we do now is that we want to do a refinement. We want to take an orthogonal representation and we want to add additional vertices and edges such that every face becomes a rectangle. Let's start with the interior face. First, for all these spans we have, we add an additional dummy vertex. And for every edge, we define here in clockwise order the corner of the edge, which is the next vertex, and the next edge, which is this one here. We now want to walk through the edges and find these shortcuts in our representation. Remember, we don't have a drawing yet, so we cannot just go here to the right until we intersect this. For that, we look at the turns. So a turn of an edge is a -1 if we go to the right, a 1 if we go to the left, and a 0 if we go straight. Now just from the turns, we want to find this front such that we can extend the edge here and get a projection of this edge onto the front. And how can we find it from the turns? Well, if we look here, we first go to the right. We have a -1 here. And as long as we do that, we only move away. So we keep counting and we add up the number of the turns until we get something positive. So we want to sum up the turns that we have. We start going to the right, we have -1, we go back, -2, -1, -2, -1, 0. We go in the same direction as our edge E prime again. And now we have another left turn. Now we get to a 1. And that means that this edge can be extended up here so that the extension of E prime projects on this edge. So as soon as the sum of the turn numbers gets positive, we can extend our edge here. Can do the same here. We have a -1, 0, -1, 0, 1. We get the edge, we can extend, and we find the projection. So -1, 0, 1, we get it here. Also here, -1, -2, -3, -2, -1, 0, 1, we extend here. And that way we continue for all the edges until we're done and every interior face here is a rectangle. And almost the same we can also do on the outer face, with one exception. There are some edges where we will never reach this point that we get a positive turn sum. So if we look at this edge here, if we move along the outer face, we have -1, -1, -1, -1. Here we are already at -4 and we look in the same direction. Now we do this, still -4. We do this, still -4. We go back, we go here, and we're still at a -4. We will never reach a positive value. And here the extension has to go to the outside, which doesn't really exist here. So we have to add something outside here. We have to add a new outer face that consists only of dummy vertices where we extend this edge to. And in this case, where we don't get a positive sum until we get back to the edge, we just extend it to the outside. So here we do this. And here for this edge, again, we never get a positive sum. We move it to the outside. Never a positive sum. We extend it to the outside and so on. But at some spots, we might get a positive sum. Here, -1, -2, -1, 0, 1. We can do the odd extension. And again, if we do this everywhere, then at some point, the refinement will have all the faces here also as rectangles. And then we get this instance here, and we run our algorithm, our ST flow on this, to find an area minimal drawing for this whole thing. And as you can see here, there's not really a way to get a smaller one here, because we have this 1, 1, 1, 1, 1, 1, 1, 1, and just walking from here, we have a path that only goes through segments of length 1. You cannot be better than that. Also, you can find a path up here that goes downwards only through segments of length 1, so we cannot have a better width or height. However, if we look at the input graph, is this really a minimum area for this? Well, it's easy to see that it's not, that we can just transform this, we can just move this up, and then we get something smaller. So this does not minimize the area of our graph. But we get a bound on the area, which is order of n plus b squared, where b is the number of bends. And in general, the compaction for a covalent orthogonal representation is NP-hard. So there's probably no hope for us to find the drawing with the minimum area. Thank you for watching.